Although you might think like, okay, yeah, I get it. Like toggle A, if A, then toggle B. I get it. I'm gonna like actually, belabor the point a little bit about exactly how these operations work, because it'll give me the opportunity to talk about like another concept that we need to talk about, which is what I would call sometimes but it's kind of like the analog of the truth table for these instructions. And sometimes we'll call it the path diagram for these instructions, or you can also call it the matrix representation of these instructions. Okay, so I'm going to go through that, and that'll be useful when we start to talk about superposition creating instructions. Okay, so let's do it. Let's just do it here. So I'll just focus on these as like the most popular and basic of all classical reversible instructions. Okay, so if I were to like extremely like belabor the point of like what is the definition of the toggle A instruction or toggle instruction, or as a reminder, it's sometimes called, not A. I could make the following explicit definition. I would say like, okay, well, I mean, I'm going to write all the possible, I'm going to write all the possible incoming basic states. So that's, it could be 0, or it could be 1. And then let me write outgoing basic states. And because I know it's a classical type instruction, it has this basic state in, basic state out property. So if you give it basic states, it'll always, return the qubit in a basic state. So I'll just write them here, like 0, 1. And yeah, I drew it in a weird way in my notes, but we could draw this like diagram. It just says, you apply it to 0, you get 1. You apply it 1, you get 0. Kind of easy. Okay, so I'll sometimes call this like the path diagram for this toggle instruction. Now, I want to make this a little bit more fully fleshed out, because one thing I want to remember is that, although the output of this instruction, these two cases, 0 and 1, these are basic states. As I mentioned last time, in general, it's possible for a qubit to be in like one of these superposition states with like, let's say x amplitude on 0 and y amplitude on 1, as long as x squared plus y squared equals 1. And as I commented last time, you should even, or can even think of like basic states themselves as like superposition states, just in kind of a little bit of a degenerate way. So let me recall that like, when you see like the basic state 0, this is really like sort of shorthand for one amount of amplitude. I want to somehow like, okay, one amplitude on 0 and no amplitude on 1. This is sort of like the full way in which, this is a valid state for a qubit. And remember, these two numbers, when you square them, they add up to 1. And similarly, this basic state, which we call basic state 1, this is like no amplitude on basic state 0, and like 1 amplitude on basic state 1. Okay, and here's where it's like a little confusing, because I mean, you have like so many 0s and 1s floating around, but they're playing like different roles, right? So like this is just like sort of like the names of basic states, these ones with the weird brackets. And these are just like regular old numbers, real numbers. Okay. So like, to say things like more fully, the toggle instruction, if you're at basic state 0, it maps you to basic state 1, which means that it maps you to having no amplitude on 0 and 1 amplitude on 1. So I'm actually going to draw, you can also draw this diagram like more extensively like this. If you're at 0, then you kind of go to 1 with amplitude 1, and you go to 0 with amplitude 0. Now this is like kind of, again, confusing because there's lots of like zeros and ones, but like this is saying if you're at 0, sort of you get amplitude 1 on 1, and you get amplitude 0 on 0. Okay? And similarly, if you start out at basic state 1, well, we kind of know you go to basic state 0, and that's like one amount of amplitude on 0, which I'll write here. And 0 amount of amplitude on 1, which I'll write here. Maybe I'll put this 1 over here. It's be a little bit better. Okay, so I want to say like this diagram like more fully specifies exactly what superposition state you go to starting from 0. And this specifies what superposition state you go to starting from basic state 1. So like this is like the most confusing diagram like so far, because there's all these zeros and ones that have different roles. But is there a question right now? Okay. So later, I'm going to like use this like shorthand convention where like this is like the most full version of the diagram, but I'll do sort of the usual thing where like if an arrow has like 0 amplitude on it, I just won't draw that arrow. Okay, and if also if an arrow has like 1 on it, I'll just not write the 1. It's like in algebra, you know, if you have like 1 times x, you just don't write the 1, and if you have like 0 times x, you just don't write anything. Same story here. Okay, and in which case, like this diagram will just look like these two arrows. Okay, and I'm going to get to it in a moment, but we're going to like do the same thing for like, let's say this operation. And so there'll be like 4 basic states that you could start in going across the top, 0, 0, 0, 1, 1, 0, 1, 1, and there'll be like 4 on the bottom. And like the diagram will become like more cluttered, and especially if you like fully explicitly write in all these like 0 and 1 amplitudes on the edges, it'll become very cluttered. So I want to show you like a different way you can organize this diagram that's a bit less cluttered. And it's to like, you can also arrange the arrows, labels into a matrix. Okay, so if you have a qubit instruction that operates on 1 qubit, so there's like 2 incoming states and 2 outcoming states, this will be like a 2x2 matrix. Okay, and here's how you got to remember it. The incoming states will always be labeled across the top on like the columns. This is like incoming. And like the outgoing basic states kind of will be always labeled on the rows. So you really think of like the action is like this. This arrow is like from in to out. And then like you put the entries in the matrix record all these edge labels. Okay. And you know, if you fully have like a diagram like this, you have like 1 edge label for every pair of incoming and outgoing basic states. So like for every entry in this table. So here, like, let me put this, there's like a 1 here. Okay, let me not circle them, but there's like a 1 here. And this 1 is this one. Okay, going from basic state 0 to basic state 1, you have amplitude 1. Okay, and if you're in basic state 0, you end up with amplitude 0 on basic state 0. And conversely, if you're in basic state 1, when you do toggle, you get 1 amplitude on 0, and you get 0 amplitude on 1. Okay, so you can always, when you see this like matrix representation, this is a matrix representation, or kind of like the truth table, if you will, of toggle. Kind of always read it column by column. Like first say to yourself, like, okay, column 1 tells me if I start in basic state 0, then I end up with no amplitude on 0 and 1 amplitude on 1. And if I start in basic state 1, I end up with 1 amplitude on 0 and 0 amplitude on 1. Question. So the question was kind of like, you know, like it was related to this question of like, here I've sort of explained how toggle works if A's value, like when incoming value is either like basic state 0 or basic state 1. And you might say like, what if it's like, not like this? What if it's a superposition state, like 0.8 on 0 and 0.6 on 1? So two things to say. Shortly, like later in this lecture, I'll explain to you like what happens when you do like an instruction like that on something that's in a superposition state. But another thing that I didn't make clear, which I'm making clear now, is as we'll see, it's sufficient to define an instruction by saying only what it does to basic states. Okay. For reasons I'll eventually say, if I tell you how an operation works when all the qubits are in basic states, that fully defines how it works on any superposition state, according to a rule which I'll explain later. And therefore, like when somebody's like defining a new instruction to you, they kind of only need to tell you what does it do to like the basic states, like what does it do to basic state 0 and what does it do to basic state 1? And then via a rule I'll explain later, you can infer what it does to any superposition state. And that's why if you sort of write the truth table or like the defining matrix for an instruction like we've just done, it's sort of you only need like one column. You have like one column for each of the possible basic states, and that's sufficient to define it. Okay, excellent question. Okay, so let me do another example here, and we'll do it for okay, if A then toggle B. So how about this one? If A then toggle B. So I mentioned the thing that people really call this is C naught AB. This stands for controlled knot. And the meaning of that is like, it's kind of like you do a knot on B, but whether or not you do it is controlled by the truth value of A. Okay, so like controlled knot means like controlling on A. If A is true, you do the knot, and if A is not true, you don't do the knot. That's why it has this name C naught. Okay, so let's draw the path diagram for this. It's pretty simple. If I were following my convention, I'd use like blue for the basic states, but let me just stick them in black. So we write down all the possible basic states. There's 4 of them because this is operating on 2 qubits, and therefore there are 4 possible basic states for them. These are incoming. These are outgoing. And I'm going to use the shorthand where we like, don't draw amplitudes of 0 and we don't write amplitudes of 1. So let's look at 0, 0. If A and B are 0 and 0, then like A is false, so you don't toggle B, so they stay 0 and 0. Okay, so we draw this arrow. And if we were really scrupulous, we'd write like 1 here, and we'd write like 0 on all these other arrows to indicate that if you start in basic state 0, 0, you end up with amplitude 1 on 0, 0, and like no amplitude on the other possibilities. But I won't write that. Okay, what if you start out in 0, 1? So then it's like A is 0 and B is 1, so A is false, so you don't toggle B, so it just stays. So you have this arrow. What if A is 1 and B is 0? Well, A is true, so you do toggle B, so A stays 1 and B becomes 1. We have this arrow. And here, if A is 1 and B is 1, you do toggle B, so it becomes 0, so you go to 1, 0. Yeah, I should always remember, like, we're writing these in order A, B, A, B, A, B. Okay, so I call this like the path diagram for the if A then toggle B instruction or the C naught instruction. And I could similarly make a matrix representation of it. It's like a bit more tedious, but I'll do it. So remember we put the incoming possibilities on top. And we put the outgoing basic states as labels on the rows. Sometimes I like to draw this arrow. Okay, and then we could fill in, we sort of fill in like all 16 amplitudes that are written in this diagram, except we were kind of lazy because like all the arrows stand for an amplitude of 1 and all the missing arrows stand for an amplitude of 0. But if we were to plunk it all in, it would look like this. We get like a 1 here, a 1 here, a 1 here, and a 1 here. Everything else is 0. And again, just like as a way to read this, what's going on with, let's say, this column? This column is indicating that if you, are doing this C naught operation, the incoming bits are in basic state 1, 0, then the outgoing state will have no amplitude on 0, 0, no amplitude on 0, 1, no amplitude on 1, 0, and 1 amplitude on 1, 1. So these matrices look a little bit like kind of like overkill for these classical reversible instructions, but when we get shortly to the superposition creating instructions where you actually have like amplitudes that are not just 1 and 0, they'll maybe be helpful for us. So let's do this last instruction here. If A and B, then toggle C. So I'll just do the path diagram here. So this is a classical reversible instruction that operates on 3 qubits. So there are 8 possible basic states: 0, 0, 1, 0, 1, 0, 0, 1, 1. Run out of room. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And the outgoing states, there's like 0, 0, 0. Okay, I won't put in the brackets, but 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And it's a pretty boring diagram, actually. Let's just think about it. As long as like, okay, if the AND of A and B, first of all, the A and B's value don't change. So whatever the first 2 qubits are, like you'll have the same 2 qubits later. So actually it'll like kind of be divided into 4 blocks based on that. And then C only changes when A and B are both 1. So like A and B are both 1 is like way over here in the corner. And when A and B are both 1, C gets toggled to 1. So we have this like diagonal arrow. We have like this diagonal arrow. And then everything else just doesn't change. Okay, so this kind of crazy thing is like the paths diagram for this instruction. And I will not draw the 8x8 matrix because that's very tedious, but you can do it. And I should mention that this instruction is also sometimes called, well, usually called CC naught on A, B, and C. That stands for controlled C naught or controlled naught. And if you think about it, it's like fun to think about it. It really does look like this. It's a C naught on B and C controlled by A. So it's like if A is true, then do C naught on B, C. If A is false, don't do anything. And then if you expand that in your mind, it's like if A is true and B is true, then you toggle C. Otherwise, you don't do anything. So that's an explanation for why this instruction is usually called CC naught. And finally, just so we're all on the same page, here I did an example where I showed the paths diagram, but I didn't show the matrix. Let me do the reverse now. I'll show the matrix, but not the path diagram. So we'll do this for the classical reversible instruction called swap. Swap AB. Let me draw the matrix. It's going to actually look like this. If you're a sophisticate, like you don't put the row and column labels in, but I'll do that for you in a second. But this is like the matrix for the swap operation. And looks kind of inscrutable, but the reason is, you remember what the incoming labels are and the outgoing labels are. It looks like this. Okay, so for example, if you do swap when A is 1 and B is 0, then the result is A is Oh, A is 0 and B is 1. So like you get all the amplitude on that and no amplitude on the rest. To be honest, it's like not genuinely so important to like remember and work with these matrices. It's like mostly important just remember like, swap, it swaps, or like how these things work. But like, especially if you read other textbooks, they'll be like talking a lot about the matrix for different instructions. So wanted to explain that.